geometric group theory. That's what I studied. One of the things that I find really interesting about that is that when you're an undergraduate and you take algebra class, you don't actually see any of the kind of stuff that I would do for research. You see group theory somewhere in an abstract algebra class. What you don't see a lot of is infinite groups, right? Mostly if you remember back to your Math 145 or whatever its equivalent is, you might have seen a few infinite groups. So most of you have seen, here's some infinite groups that we could all say we saw. These are sort of, infinite groups everyone sees. Meaning everyone, everywhere on the street with me. Right? The integers under addition. I think we can all agree that's a group everybody's seen and it's an infinite group. Right? You're probably okay with me using the rationals, the reals, the complexes. Maybe let's throw in a matrix group. Okay, because if you're a math major, you've at least seen that one under matrix multiplication. Or SL if you don't like GL. Right? The invertible n by n matrices over the reals with determinant 1 if you want, or just non-zero determinant. Right, so these are some infinite groups, but usually when you see them in Math 145, this one you see specifically to point out the difference between a finite cyclic group and an infinite cyclic group. And that's it, essentially. And then you look at the integers modulo n and you play around with finite groups, right? This one you just see as an example where, okay, we have to think a little bit about what we learned about the rational numbers a long time ago. We have to think about whenever we define a function, say, on the rationals, we often have to think about the well-definedness of it. At least that's the way I teach it in 145. Is I think, well, this is a good example of sometimes if I wanted to find a function on Q to somewhere else, and I want some formula that takes in a fractional represented with a particular rational number equals whatever, I have to think about the well-definedness of a function. It's kind of our first example of looking at equivalence classes and trying to define functions on a set of equivalence classes. That's the way I kind of present this example in abstract algebra. And it's one that you're supposed to be familiar with from, like the 3rd grade. And then there's this one, which everybody, because Math 46 is a prerequisite for Math 145. Everybody's supposed to know that. Although they cringe as soon as you say it. They're like, ooh, I'm supposed to remember something from 46 in here? Or in fact, then you point out that in fact any vector space under vector addition is also a group. And they're like, no, I don't remember that either. All right, so those are the infinite groups, that pop up at the beginning of the class, but then most of the class is spent talking about finite groups. So one of the things I want you to believe is that sort of what I want to express is that the fundamental questions about infinite groups, I mean, this is pretty obvious, but I have to say it, are pretty different from the questions about finite groups. Probably an obvious statement about finite groups. So what do I mean by that? So I'll write up a few things, and I'll say what these words mean in a little bit, but I'm going to give some examples in a minute. But things like, what does it mean? So G is an infinite group. Here are some questions you would ask about an infinite group that you wouldn't ask about a finite group. Is G finitely generated? I'll explain what that means in a minute. Is G, if you don't remember, you'll remember it in a second. Is G finitely presented? That's probably one you don't remember, maybe. Does there exist, let me say it this way. Does there exist G in G of finite order, right? Or here's another one. Could every G in G have finite order? Right, so those are just some questions you wouldn't even ask about a finite group. All finite groups are finitely generated. They're all finitely presented for stupid reasons. Once you see the definition, you'll be like, duh. And then everybody has finite order. That's one of the first things you prove in Math 145 is that every element of a finite group is killed by the order of the group, if I do the operation that many times. And this one's a doozy right here. That's a really nice question about the existence of infinite torsion groups. Right? There's still an open question in group theory about this piece. All right? So, those are some questions you'd ask about an infinite group. So probably not surprisingly, the techniques you use to study infinite groups are totally different. Than what you see in something like, a Math 145, an abstract algebra 1. As an undergraduate, or maybe even as a graduate student. In fact, I don't even know what we have in our first year algebra course here. I'm not quite sure if we ever get to any decent infinite groups in there. Right? So first of all, that's the first thing I want to point out, is that geometric group theory is about studying infinite groups, and a particular kind of infinite group. Geometric group theory is about studying infinite groups that come at us from geometry and topology. So there's two places. So where do these groups come from? Well, they come from geometry and topology. In the form of, say, the fundamental group of an object, right? The fundamental group of a topological space. Say, of a manifold. Right, so those are generally infinite groups. I mean, there are some that are finite groups, but generally, so if you need a particular example, so for me, when I look at the free group on two generators, which I'll say what that is in a minute, I'm really thinking of that as the fundamental group of this space. It's the wedge of two circles. All right, so it's the set of all ways that I can map circles in there continuously. There's lots and lots of different ways I can do that. All right, or the fundamental group of a surface, or the fundamental group of a torus. That's z plus z. Okay, so there's some that come from topology. If I want to think about geometry, I might be thinking about discrete subgroups of the isometry group of a particularly nice space, like say hyperbolic space. Those kinds of groups, all right? So an example of one of those might be, the fundamental group of a surface of genus G, where G is greater than or equal to 2. Any one of those is a discrete subgroup of the isometry group of H2. So those are the kinds of groups that I study, all right? But also, another place, there's sort of geometry and topology, that's one of the places, and then the second place is combinatorial group theory. All right, and I'll say what this is, and I will put up some definitions in a minute. This is just sort of an overview. This is where you study groups. I'll study finitely presented groups, so study groups G that are described using a finite presentation. And I'll remind you of what this is in a minute. But the big idea, by putting up these two viewpoints, is that what geometric group theory really is it's a way of passing between two worlds, using geometry to study groups and using groups to study geometry. All right, so here, these groups come from geometry and topology that we're staring at, and we somehow want to understand the structure of these groups by knowing that they came from a particular space. All right, I'll make that more formal in a minute. Over here, what you do is you can construct groups in some sort of abstract combinatorial way. You're just going to describe a way of building the multiplication table for a group by a finite presentation. Okay, it's going to be an infinite group, but that's okay. You're just describing a way of thinking about the structure of that group in a combinatorial way. And what you might want to do is build a space that models this group. All right, so it's not necessarily going to be a manifold, it's not necessarily going to be HN, but this is another thing that happens in geometric group theory, is that you either know what groups you want to understand and you use geometry to understand them, or you're saying, I'm looking at abstract groups, and to understand those groups, I need to build a space on which the group, sort of a geometric model for the group. So, let me give some terminology, some real terminology, some definitions. So let's go back and think about finite generation for just a minute. So what does it mean for a group to be finitely generated? So G, well first of all, G is generated, so let S be a subset of a group. Well let me say this, because for those of you who hate algebra, which I'm sure there's at least 5 or 6 people in the room that would totally jump in that camp without even thinking. It happens everywhere you go. Any room you go into, there's going to be 5 or 6 people that hate algebra. But, so here's a fact that again you were forced to stomach in an undergraduate algebra class. Here's a fact. Is that, that if I look at the symmetric group on n letters, so remember what that means, that's just all it's the set of bijections from a set of n elements back to itself. So this is a finite group, right? It has n factorial elements. And the operation is composition of functions. All right, so that's a group. And one of the facts that you learn about this group is that every permutation can be written as a product of transpositions. Right, one of the most hated proofs in all of Math 145. That's not the most hated one. The most hated one is the odd even proof. Right, that once I can write it as a product of transpositions, in some way, the parity is unique to that element. The parity of the way I can do that. That's the most hated proof. All right, but this is getting at the idea of what it means is that I have some special set of elements, the set of transpositions, in this case. And what I see is that every element can be written as a product of that smaller subset. All right, so, of course, again, this is a finite group, so finite generation wasn't a problem. I could have just put everybody in the generating set. But I have a smaller set of elements that generate. Even for a finite group, the idea of having a smaller finite generating set makes it easier to study the properties of that group. So the idea of finite generation, whether it is finitely generated or not, is maybe not a great question for finite groups because they're all finitely generated. But understanding what generating sets are out there is a good thing. So you also learn that every permutation in Sn can be written as a product of disjoint cycles. You also learn that fact. So there's another generating set for Sn. And in fact, you can generate Sn from a set of 2 elements. So there's lots and lots of different generating sets for a given group. All right? So that question is actually a little more subtle than I said. But just the question of whether you're finitely generated or not doesn't mean that much for finite groups, but it's something you have probably seen before. And so knowing whether you're finitely generated is one thing, having a decent generating set is another. So even for infinite groups, I could first ask whether I am or not, and then once I am, I decide who's a good generating set and who isn't. Okay? So how would we decide this question for an infinite group? The question of whether you're finitely generated or not. So I'm going to give you a non-traditional way of deciding whether an infinite group is finitely generated. So let G be an infinite group. And let S be a subset of G. I'm going to ask a slightly different question. I'm going to ask you, so let this be a finite subset of G. Just pick some random finite subset, and I'm going to ask, does S generate G? So what do I mean by that? So you can think of it this way. Can every element of G be written as a product of elements in S with maybe their inverses too? Right, so really I'm thinking, when I put these little brackets around it like that, right, I really have to include the subgroup generated by S, meaning the smallest subgroup of the group that contains the elements of S. So you can think about it that way. I can throw in the inverses. Can every element of G be written as a product of things in S or S inverses? That's what it means, okay? How do I answer the question? Well, if you're a combinatorial group theorist, or you're in Math 145 and it's a homework problem, you just try. You just go and you say, oh, I don't know. How do I do that? Or you cry, or you go and Google it and hope it's on Wikipedia, right? Those are the things that we do if it's a homework problem. But what do you do if you're a geometric group theorist? You try to find a picture that will answer the question for you. So that's what you try to do. So here's the answer I would give. I'm going to say this. I'm going to build a graph. Which sounds like a complicated way of doing this problem, but I can't do anything without building a graph. I don't do anything in my life ever without building a graph. All right? So how am I going to do that? I'm going to let the vertex set be the group elements, the whole group. All right? And I'm going to have, here's how I'm going to define edges. So V and W, this is an edge. If and only if, V, W, if I get this right, I'm going to get it wrong. I know I'm going to get it wrong. V, W inverse is an S. I'm going to do this the wrong way. Have I already done it wrong? Let's see, no, what do I want? I want, that's right, all right, good. I thought maybe I put my inverse on the wrong side. This is what I want. Or I guess, yeah, I want to say it this way. If W can, this is actually a better way of thinking about it. Either one, because I can put the S inverse. So if they differ by a generator. Okay?
Now you have the inverse.
Now I have the inverse on the wrong side. Let me say this one. Now I do, wait, it's, yeah, you're right. No, I want it that way.
Yeah, that's fine. You just wanted your other thing.
That's right. The other one. All right, and now here's my claim. Is that G is generated by S if and only if this graph is connected. Okay? So it's a very strange way to think about finite generation for somebody who comes from Math 145. Because it doesn't have anything to do with, it doesn't look like it has anything to do with writing elements as a product of something. But it allows you to start visualizing a picture where we take our group elements and we dot them somewhere, right? And then we're going to build some graph. And the question of finite generation comes down to whether the graph is connected or not. Okay? So that is the geometric group theory. That's the GGT answer to everything. Build a graph. Okay? The same thing is true about finite presentation. So, well, before I go on to finite presentation, let me just say that let's just say we do have, now let's say, okay, the answer was yes. Let's say, okay, I picked some really nice generating set. I actually picked one for which this graph is connected. Well then, what I get is a connected graph. So now suppose I'm in the case where S does generate. For some group G. Then this construction is called the Cayley graph of G with respect to S. Right, usually the standard notation is something like this, or something. Some people use the letter C for Cayley. Now it turns out that if I make each edge have length 1, I can put a metric on this graph. On this connected graph. And so I can put a metric on there. What do? The distance between 2 points is just the small. I can think about it really as putting a metric on this connected graph, or on the vertex set of this connected graph, if that's all you care about. I can really think of it, how close are two vertices? I look for the shortest edge path. Right? So I'm just counting the number of edges between two elements. So I can put and then when I do that, what do I get? I get a metric space. In fact, a proper geodesic metric space. I don't know what those words mean. Page 5, write some math order. And my group G now actually lives inside of the isometry group of this metric space. All right, so it's getting closer to what the examples I said at the beginning. Right, the examples I said at the beginning is I look at basically discrete subgroups of the isometry group of some nice metric space. Essentially, all the examples I put up were like that. And so now I'm saying that if I'm willing to make my metric space a graph, I can take any finitely generated group and think of it that way. So any finitely generated group can be thought of just like, a lot of the groups that I put up at the beginning that are classical groups that come from geometry and topology. Okay, so that's a good thing. We're thinking of now a group of isometries. That's much, much better than just, for a geometric group theorist, than to just play around with symbols and do multiplication in a group. Right, now you can think about things moving around. You have a symmetry group of some sort. Now notice this idea works really well even back for finite groups. If you look over here, you can build a Cayley graph for this guy using this generating set. It's a finite group, but that's still totally okay. Right? You can do that. In fact, what you could do is just do the ones that are, instead of using all transpositions, if you go like this, if you look at the adjacent transpositions, so 1, 2, 2, 3, those ones, that's an even smaller generating set that generates the symmetric group. If I look at the Cayley graph for the symmetric group with this generating set, I can see that horrible fact that I didn't like from Math 145, right? That if I can write sigma as the product of 7 transpositions, then any other way that I can do it, it has to be odd. That's the fact I'm talking about. Everybody remember that? I'm seeing like pain, I'm seeing stomach cramps all over the room from Math 145. If you use this Cayley graph, the one with adjacent transpositions, that fact just becomes showing that that's a finite graph. You can actually just draw it. That fact comes down to showing that that graph is bipartite. That's it. That's there's the geometry of the problem. I draw the Cayley graph. You can just see it. In fact, you can do this proof inductively. I had an undergraduate write this out. For an undergraduate honors thesis was to do that. Was to combinatorially describe this for every n, and then prove the horrible fact from Math 145 by showing that it's always bipartite. Right? So that means that's a really nice way of seeing that. So why is building this graph, why does it say anything about the group? So notice some things about the Cayley graph right off the bat. What can we see in a Cayley graph? We can see a lot, right? So one of the things we can see is so there's a vertex corresponding to the identity of the group, right? That's a vertex, so this is a group, so it has some identity. And then there's all kinds of other vertices. But I follow along edge paths, and one thing I can see is if I can see closed loops in that graph, closed loops correspond to words in the generators whose product is trivial. All right, so that's one of the things right off the bat you can see from a Cayley graph. If you can draw any part of the Cayley graph, that's one of the things you get for free. All right. Oh, so how does that relate to this question that I said over here about Math 145? Well, the idea is if I had some sigma, I want to think of that as a word in these adjacent transpositions. So I'd have one way of writing it. There's my sigma, there's the identity, and these along here are some of these transpositions, say alpha 1, alpha 2, all the way up to alpha n minus 1. Right, these are some alpha i's along here. That's one way of doing it. If I had another way of doing it, then there's the other way of writing sigma, so I'd have a closed loop. And if I'm bipartite, I can only have closed loops of even length. And that's why the Math 145 problem is solved by looking at that question inside of this particular Cayley graph. If you used a different Cayley graph for Sn, you wouldn't get that Math 145 fact. You'd get some other Math 145 fact about Sn that you could probably draw a picture for. Right? So that's something really cool that you can see. Let me give another example of Cayley graphs, since I've only given one. How long have I been talking, Andy? Am I still on high def?
Yep.
Since I have no stopping place, no natural stopping place in my notes.
You might want to quickly say, people might not know what bipartite means.
Oh, bipartite. So you could take as a definition that all closed loops have even length. Take that as a definition. Or, so a bipartite graph is one in which I can take the vertices and partition them into two sets. So there's my graph. It has a vertex set and it has an edge set. I don't want to use the letter G. This is a graph. I'll use that letter G. There's a vertex set and an edge set. So my vertex set, it's a disjoint union of two sets, and all of the edges go from A's to B's. Right? There's no edges within A and no edges within B. Right? That's the definition of bipartite. And it turns out it's equivalent to what I said about loops, closed loops of even can only have even length. That's a Math 22 problem. All right. But I think that's kind of a cool thing. So that's finite generation. I want to bring up I kind of want to talk about finite presentation, but not really. All right, let me put up another example. Let me put up two more examples of infinite groups and Cayley graphs. Examples, the two that everybody has to do. Everybody has to see them. How much time do I have?
Like 15 minutes, 20
Okay.
minutes.
You can go till 1.
All right.
Well, there's,
Not with this HD, I can't.
right.
Oh, I see.
So I'm going to put up the free group on 2 letters. I'll draw the Cayley graph, and then you'll know what group I'm talking about, I think. Everybody's probably seen, well, maybe not everybody's seen this picture. Or maybe you've seen it if you're taking one of the geometry topology classes. I'm guessing you've seen something like this. I hope. Anyway. Right, so it's hard to stop drawing it once you start drawing it. Like one of those OCD things. All right, so here's all the vertices of the graph. But the way you should really think about it is I give some name to the generators. So it's going to be generated by 2 elements. And I just want to look at all possible strings in A's and B's and A inverses and B inverses. That's really what the group is. It's a set of words that I can write down in A, B, A inverse, B inverse. I have to be a little bit careful, and not very careful at all today, but it's basically the set of words in A, B, A inverse, B inverse, where I really mean reduced words. So what does reduced mean? It just means A never sits next to A inverse because that's a stupid thing, right? And then I never have B sitting next to B inverse either, all right? So if you think about the reduced words, it means I'm not just going to go like A inverse. I'm not going to do a backtrack like that. I'm not going to do that. And then B there. And then my operation is concatenation and reduce again. Right? I stick 2 of those together, and if there's some reduction, it's going to occur right in the middle, and I just reduce. That's the operation. All right? But again, you can also just think of it as the fundamental group of the figure 8 knot. I mean, of the figure 8, not figure 8 knot, figure 8. Right? That's one example, and there's a Cayley graph. So notice here, the Cayley graph is a tree for this generating set. The generating set, that's a tree. That is a particularly nice geometry. Really nice geometry. And then, of course, the other example also has a nice geometry. Is Z plus C with the standard generating set. Plus or minus 1, 0, and 0 plus or minus 1. The standard generators and their inverses, and then I get just the integer lattice. Okay. There's the vertex set. And so you can see the fact that in this group, I have that if I call these guys A and A inverse, and B inverse, I have that if I do A followed by B, it's the same as doing B followed by A in this group. Because if I do A and then B and then A, mark that as the identity, then this is A, and I have a B edge. A followed by B is the same as B followed by A. So you can see the commutativity in the graph. All right, so that little guy's a closed loop. Over here, you can see the freeness of this group because I have a tree. I have no relations, no closed loops means there's no relations in this group. No closed loops means no relations. In this group.
Non-algebraic relations.
So what I mean, there are no algebraic relations. What do I mean is I mean that anytime I write down a reduced string, if there's any letters in it at all, it's a non-trivial word. And the only way of writing the identity in this group is using the empty string.
This question is more as opposed to transcendental relations.
Oh, right. Oh, I see.
Or does that just mean like not reduction?
Yeah, I mean not reduction. I meant out, yeah. So I was sort of saying that this geometry means this algebra. Right. All right, so you might think, well, so what you've done by becoming a geometric group theorist, what you've really done is become a graph theorist. You might think that, but that's not actually true. Right, so these graphs are kind of, it's not really just the graph, and you don't study these graphs like you study a graph in graph theory. The way you study these graphs in relation to the group is as a proper geodesic metric space. You really want to think of this as some sort of discrete model of a geometry that you don't have on hand. Right, so like here, you want to think of this really, why is it that this should be the right Cayley graph for this group? Is, well, that guy already occurs. This guy's already living inside of the isometry group of Euclidean space. Right? This guy's already living inside of there. So this graph is just some discrete approximation to this geometry. That's really all it is, okay? Now, in general, what you have is, if you have some finitely generated group that you don't recognize, and you draw the Cayley graph, it's a discrete approximation to some geometry you don't have. So you have to rely on, then you really have to think about the geometric properties of this graph all on its own. All right, so one thing you can do is, let's see, you can detect, so in the Cayley graph, I have so many more things I wanted to say. Like you can see, I have all these notes, but I'm not going to get to any of them, and I'm not going to have a natural stopping place. Actually, what I really wanted to prove, I wanted to prove something. Should I prove something, or should I ramble on?
Just stop at CB wise.
Get stuff at CB wise. Well, here's what I want to say. I want to say this. Now that I've gotten this far, I want to end with an open question. That's one thing I want to do. I always want to end with an open question. So in exactly 4 minutes, I'm going to end with an open question. Here's what I want to say. I won't say that. So you might, I should say this. Observe one thing. If I change my generating set, it seems the graph changes drastically. That seems a little scary. Right? But it turns out that's not such a big problem in this theory. It turns out that it does change drastically, just like I said, even for the symmetric group. If I look at the graph of transpositions, with adjacent transpositions, I see this beautiful fact about the symmetric group. But if I had looked at a different Cayley graph, I wouldn't have seen that beautiful fact. I would have seen some other fact. So you do get a drastic change. For finite groups, it's as drastic as I just said. You will see something completely different about that group. For infinite groups, it turns out that it's really not that big of a deal for infinite groups when you change the generating set. Because it turns out that when I view the graph, as a proper geodesic metric space, like I said. So these words, proper geodesic, I just can't help but write them. You can ignore them. Like, it's just, that's my world. You can forget about them. If you don't know what they mean, it doesn't even matter. Proper just means I have a finite generating set. Geodesic means I can connect everybody, basically, for today. That's all it means. I mean, I could give the definitions, but it doesn't matter what they are. All right? For this talk, it doesn't matter. So when I view the graph as a proper geodesic metric space, the change of generators only changes the geometry up to what's called quasi-isometry. So it really so again, if I'm thinking, oh, I've got a metric space that I've built from a generating set, when I change the generating set, I get a different metric space. So instead of thinking about changing the graph, think about I've changed to a different metric space, right? But it's not that big of a change. It only changes up to quasi-isometry. So that's a little bit like isometry with some linear distortion. That's all it is. So this is like a linear, I can write it up. So here's what I mean by quasi-isometry. Between two metric spaces is that the distance measured in y between q of x, q of, let me say a and b, is less than or equal to lambda times the distance measured in x of ab plus an epsilon. I could use lambda again. So it's a linear distortion of the metric, all right? And then there's this business about a plus epsilon. It's not quite by Lifshitz. It's not really just a scaling on either side. There's an epsilon. So for example, I need one more thing to have quasi-isometry. I also need to know that the distance between, it's almost onto. So there exists constants lambda. In fact, I only really need one constant, but I'll just do the standard definition. So this is like linearly distorting the metric and almost onto it. Right? So for example, it turns out over here that this graph, this is a very weak notion of equivalence for metric spaces. Over here, this graph, the Cayley graph of z plus z, with respect to that generating set, is quasi-isometric to actual Euclidean space. All right, so this is a really nice, beautiful metric space. This is a graph. And these two are actually quasi-isometric. Because that little epsilon means I can sort of ignore little pockets of size epsilon. I don't really care what happens in them. Epsilon being the area of one of these squares. And the lambdas mean, well, okay, that was square root of 2, but now I'm going to call it 2. Right, that's it. That's quasi-isometry.
Squint and zoom out.
Squinting. Drink a lot of beer and look at the two spaces and they look the same. Right? That's what it means. That's really what it means. But you might think, gosh, that's really weak. But what's the most cool fact about geometric group theory is that notion of equivalence actually preserves a whole lot of information about the group. So the notion of quasi-isometry actually preserves a lot of group theoretic information. Like whether you're finitely generated or not, whether you're finitely presented or not, whether or how you can solve the word problem in that group. Those are things that, it doesn't matter because now in the last 3 minutes I can say whatever I want. The sort of amount of time it takes to solve the word problem in your group, or the isoparametric inequality if you want to think about that. There's lots of things that are preserved, whether you're one-ended or not. So lots of different structural properties about your group. It turns out you can use any Cayley graph you want. Or, in fact, any metric space that might be quasi-isometric to your Cayley graph. And that's another viewpoint of geometric group theory, is if the graph isn't good enough, go to your favorite space that is quasi-isometric to your graph and work in that space. Use the properties of any differential geometry you might know in that space. And then you can bring it back to your graph or bring it back to your group using a natural quasi-isometry. All right, so in my last 2 minutes, I'm going to leave an open question because I think this is good for graduate students. So now you're supposed to think, wow, geometric group theory is the coolest area in town, which it is. But here's an open question.
Even though you wrote those inequalities.
Even though I wrote those inequalities, why did I write them wrong?
No, it's just you were doing so well, now it looks like analysis.
Yeah, that's right. Yeah, I know, I didn't want to do it. I didn't really want to do that. You're right. Nor did I want to use, because now I've done technical. I've actually given a technical talk. That's why I used epsilon. I've given a technical talk. The open question is, this is a huge open question. I'm going to say it very vaguely, but understanding the Cayley graphs, the geometry of the Cayley graphs for groups like this. Here's a very harmless looking group. F3 semi-direct group. So I did the free group on 2 letters. You can imagine what the free group on 3 letters is. Right? I just can't draw a valence 6 tree. That's just me. But it's that same picture. And I have a semi-direct product. So first, forget about what that is for a minute. Remember what a direct product is. Everybody probably remembers that. Right? So for a geometric group theorist, I'm thinking tree, I'm thinking line, I'm thinking tree cross line. That's what I'm thinking. Right? That's the picture in this group. In fact, if I do that, if I actually take a valence 6 tree, and I take the direct product of it with the real line, I get a tree cross R, and I just look at the one skeleton of that thing that I just built, just look at the graph part that I just built, I get a Cayley graph for that with a standard generating set. Okay? So what is this group? Well, all I've done is I haven't done a direct product, I've skewed the product somehow by a particular automorphism of F3. So I'll just say what that is in the last minute. I'll say just what the semi-direct product is. It's just a crazy way. So remember, again, in Math 145, you construct direct products, or you say, okay, a group splits as a direct product if I can find 2 subgroups, both of which are normal, and their product is the whole group. Right? I multiply the 2 subgroups together and I get the whole group back. So that means every element's the product of those 2, and I have this normality condition. And they intersect trivially. Right? They're non-overlapping. So this construction allows just for one of the factors to be normal. Right? And there's a construction. So how do you do it? Well, you take the same set. So F3 semi-direct Z as a set is just equal to the same thing. It's the ordered pairs. It's A, R, or A, N, where A is in F3,
and it's integer.
And then I just have to tell you what the product is. And so I have an A, comma, N, and I have a B, comma, N, and I'm going to multiply them together. M, thank you. That's a 145 mistake when you don't change variables. Right? When you think they're all called N. And then here, instead of doing A times B, I have to do A, and then I have to let N act on B. Right? So I have some automorphism of F3. I have a particular automorphism of F3. This guy's generated by 1. I have a particular automorphism. What I have, so I know that phi is a single automorphism of Fn. So let me get this right. I'm going to do what? It's going to be phi of. Wait, I did something wrong here. I really want N to act on B. So what do I mean by that? What I mean is that I have a generator 1 here, and I want to have homomorphism of Z into the automorphism group of F3, where 1 goes to phi. Right? That's what I want. So for N to act on that, I really need phi raised to the N applied to B. Good. All right, so here's a new product. It's just some crazy product. So it turns out these groups are potential counterexamples to absolutely every question in geometric group theory. Like just F3 and like pick your favorite automorphism that's not stupid. Like I don't want one for which the power of its inner because that's stupid. If the power of its inner, then I'm basically looking at this group. Right? So but if I pick like an interesting one, an interesting automorphism, then these groups are really the potential counterexamples to every single question that you could ask me in geometric group theory. And it's really, a lot of it is just trying to understand the structure of the Cayley graph, right? It's a fairly simple, topologically, it's a tree cross R. And all you've done is somehow twist that R factor around there, right? So that's my open question. And I think that there's lots and lots of work on understanding geometry of these groups, but again, nobody knows. I mean, they've already been proven to be counterexamples for lots of things, but they're also potential for all the other open questions. So I'll end on that note. Thank you.
Those groups have that many but Z2s, don't they?
They can. Those groups can, they don't all have Z2s. So if I do F2 semi-direct Z, they all have Z plus Z's. And again, if you're a topologist, the way you think about that. So here's another way to think about these groups. Think about a surface, a punctured surface that has fundamental group F3. And now, this is just the mapping torus. The fundamental group of the mapping torus for a particular homomorphism with that surface to itself. So for F2, you're looking at a punctured torus, and you're going to do some homomorphism of that, and you're going to look at the mapping torus, and you can see that the bounding circle is always going to create a Z plus Z in a semi-direct prime. So there's a topological proof as to why F2 semi-direct Z's are all have Z plus Z's. There are examples of these that are hyperbolic groups. So they don't all have Z plus Z. I know,
But
it's
no,
totally
we're
insane.
not cat zero.
There's lots that aren't cat zero. There's lots that are cat zero. There's lots that are hyperbolic. And the ones that are hyperbolic are potential counterexamples to the I'm hyperbolic yet I'm not cat zero question. So they're yeah, I know. It's like, it makes you want to cry. But that's the nature of the beast.
So ones that are hyperbolic but not cat negative 1.
So for hyperbolic but not cat negative 1, I believe there are known examples. For, well, maybe not, that's not true. It's that you're hyperbolic, but maybe you're not like two-dimensional cat minus 1. I think Povich has examples like that. But I think, yeah, so I think that's like for everything. Those guys are crazy. And they look so harmless. They look so harmless and safe and friendly, but they're not. All right, that's that. Any other questions? Makes you want to go back and take Math 145 again, doesn't it? With a whole new perspective. Let's draw Cayley graphs everywhere.
Kim, what's your favorite math book?
My favorite math book? You besides Brad's and
What's your favorite? How most
Actually, that's like, that book is more like a curse, right? I mean, the Brad's book is, let's see, there is a favorite math book of mine that I cannot get anymore. And it's Alan Bearden's book on discrete groups of something. I can't remember the name of it now. It's Bearden's book. That's one of my favorites. I really like that book, and I never got a copy of it. I never stole a copy of it from anybody in graduate school. And now you can't get it anymore. That's one of my favorites. I don't know what other favorite math books I have. All the ones that I